Hello everybody. It's going to be a lesson today on improvement of classification results. So we're going, in a sense, through practices of individual components when you're doing a classification script or a classification workflow. So roughly we'll have one that is on the data that we use for classification, test data. One is a demo of the stratified shuffle split, an extremely convenient function provided by Scikit-Learn. And we'll have a look at the multiple classifiers that are available from Scikit-Learn and how we can use them in conjunction together to see which one is better and which one is worse for a specific task. So our first exercise is I'm going to explain a little bit about a certain functionality that I'm using in the material for this lesson, but that might not be so obvious how to handle. It's about how to create test data for a classifier. Also later, if you want to do unsupervised learning, the same test data for anything. Test data of the type that Scikit-Learn uses frequently to demonstrate some properties of its classifiers, clustering algorithms, and so on. And particularly, we want to be able to create complicated test data, so where we can specify mathematically what complexity actually means in order to be able to sort of, if we have a hypothesis about what our data might be structured, then we can convert that into an algorithm that produces test data that are of that kind. And what I have prepared here is a function that I think you have it also in the materials. It's data on a torus. And it's labeled data for classification. So we need to get the data, but also the labels. In this case, it's two labels, 0 and 1, simply. And it's a function. So you can see def underscore and then a function name. So that means it's something that we only need to execute. And then the whole function will be available for performing, but nothing else happens. So there is also a large number of comments here that you're welcome to read through, and then the function itself, very complicated. And we'll have a look at the data first, and I'll comment on the function at the end of this exercise. I'm now starting to be very lazy and starting to copy and paste code. So I will try to make sure afterwards that you can also download this exact code that I'm using here. There might be some modification to what is on the website for download, but will be very similar. So here's the code. So you extract features, your data, samples and features X from the function. You also get the labels directly, similar to what you have maybe seen when you have done the materials. And then you specify a couple of things, the first of which is the number of samples. So if you like, the number of rows. The number of features is not up to you. You will just get 3 features because that's how it's set up. It's a 3D data set. And 3D meaning 3 columns in your data frame. And then you have a factor of 0.6. I'll show it maybe later what it means. Just the relationship of the labeled 0 data compared to the labeled 1 data. And finally, the noise level, to say it's a deterministic rule. It makes a perfect shape. If you want to make it a little bit more blurred, then you can add noise of random numbers, use it to blur the image as much as you like, sort of to make the classification algorithm as difficult as possible for the classifiers. And then it's just, once you have X and Y, you can just plot them. And if I'll just get this function in axis in, then this code will help us display the data. And so you can see this now not quite trivial. It's not like we did with random numbers when we chose two different means, which is that we have one distribution here, one there, and it was easy to see where the line is that splits them into two. It's very complicated because this is now sort of involved. I don't know if you can imagine it already from a static image. Sometimes it's better to animate, but here there's a torus within a torus. Do you know torus? It's the bagel or the donut. And there's a blue torus, which is the big one. And there's a red torus, a small one, a thin one, which is embedded within the blue one. So it's not so easy to actually separate the red data points from the blue data points unless you find out that your data have this kind of toroidal topology. So for visualization, maybe you're interested also in using it, applying this. The code is just a scatter 3D. So 3D, we have three features. So X, Y, and Z coordinate, and scatter 3D, you just put X, Y, and Z coordinates one after the other. Very similar to scatter 2D or scatter that we used already, just one more feature. And this last method here, view init, if you can see that, that is the angle where you can rotate to coordinate system. So you should learn it. And it's easy to understand. I've used 30-30 to get a kind of an inclined coordinate system. The first one is to incline the coordinate system forward or backward. Well, at least we imagine it like this. It's only a 2D projection anyway. So if you just do it, make it 0, then it sort of pushes it backward and you see it from the side. And if you were to make it 90 degrees, then it sort of all comes into the front of you and you look at it from the top, right? So then how you can adjust this sort of backwards, forwards inclination, and 45 is somewhere in the middle. And now you can start already by playing with this. You can already imagine better how that red torus is embedded within the blue torus. And similarly, if you want to go from a rotation that goes in the plane, like left-right rotation, then if you just put this 0, then you put it on one side, make that 90, sort of turn it 90 degrees around, put it to the other side, as if you would walk around that cube. And what we did, this 30 was somewhere in the middle, so we get a nice view of this torus. So that's about it. I just wanted to demonstrate that you can create arbitrarily complicated shapes. In this case, only you need to know how to define the coordinates of a torus, and then you do a smaller torus and a big torus, and you mix them together, and that's it. So that's enough, but I want to show just one more feature. How does this function come about? So if you have looked into the materials, there's a function that's called make circles, right? Probably you have used it. If you have already done some of those things, you have used make circles. And actually, when you look at the description here, where does it say? Does it say somewhere? It's nothing but, this function here to create the torus is nothing but a modification of the code that Scikit uses to make circles. Right? Circles was in the plane, gave you two features, and is used in many things. Dataset makes circles. And if you go down, then you will have a lot of demos in Scikit-Learn uses those circles to create data to see where algorithms fail and where they pass. And so what I have used is I have taken advantage of the fact that Python, of course, is open source. Everything here in that language is known, right? It's all public. You can get all this. So I just want to show you how you can actually see that code. So if you find a function like make circles, which I just imported, it's called make circles, and you get it from scikit-learn.datasets. What you can do is, if you want to know what the code looks like, sort of that underlying, that creating those, like what I had up there to create the torus, too complicated to explain, but the actual Python code. And what you can use, what you can do is you can use inspect. So if you import inspect, then the function source, that's sort of the source code that is underlying a function, you can get it from inspect using the method getSource. Right? So getSource takes an argument, which is the function. So you're interested in make circles, you get the source of make circles, and you put it into a function source, into a variable, and then you can just print that function, and what you get is an output, is sort of an ASCII version, a plain text version of the code. So as you can see, it's a Python function. I'll just make it bigger here. Def, so function definition, it's called make circles. That's how you call it when you import it. And then it has ensamples, shuffle, noise, random state, and so on, things very similar to the torus function above. But after the explanation, then somewhere here, where is that? It actually starts as the actual code. So it makes some checks, whether you provided the right input arguments, and then it gives you all the things, how to calculate using, what does it use? Linspace and cos and sine to make circular functions, and the inner circle and the outer circle, and how to get the labels from it. And that returns you X and Y, right? Which is convenient because then we can do all our machine learning. So just to highlight this, if you use inspect, that little code, inspect getSource, you can see what is underlying a given function, for example, make circles. Right, so that was more of a curiosity, but here comes a very important thing when it comes to machine learning, namely the stratified shuffle. Do I see a typo here? Shuffle in English. It was written in a German way. Here it's maybe more in an English way, the stratified shuffle split. And what we want to do is we want to start now. Actually, as you can see, we import make circles. So just use that function make circles to create data that lie on two circles. It's an inner circle, which is the red one, and an outer circle, which is the blue one, and here heavily contaminated with noise. So if you don't believe me, make that 0. Yes, they lie on perfect circles. And if we contaminate with a good noise level, then they sort of scatter around and they make nice distributions. We can check the histogram, what that all looks like. The feature that we want to look at here is the stratified shuffle split, namely the division, like you have learned it, that we need to divide into train data and test data in order to use part of the data to train a model and use the rest of the data in order to predict and see whether the model got it right. And the strain shuffle split does that for you in many instances as you like. So it takes the same data set and it splits it in train and test data, but it does so in a randomized fashion such that you can produce multiple realizations. So you can repeatedly train the model on different splits, so to speak, and then check whether the way in which you split the data actually affects the outcome, because you want to be as robust as possible, right? You don't want to depend on the fact that you took the first 70% of the data for training and the last 30% for testing, because there might be a bias in the data, like the famous papers where machine learning was criticized for just picking up biases, where they used lab data from a hospital, and it turned out in the end that the first half of the data was done by a different technician compared to the second half. And so there was a bias in the data, and the machine learning model actually only picked up that bias and didn't really properly predict the features they were after. So in order to avoid this, the stratified shuffle split is an excellent tool to do so. And it works in the following fashion. So let me just copy and paste the code and have a look at it. What does it do? You create by calling the function that I generated. So I had made a generator here from SSS, the stratified shuffle split, when it was initiated. Where did I initiate it? Well, I didn't, so it will not work. I need to do that. It's this here. We want to import the function. It's a stratified shuffle split, and it's a class from which you create an instance, SSS, which is this one here. And it takes 2 arguments. You define how many splits do you want. So just how often do you want to have a train test split, like 10 are used in this case just, and you use the test size. You define how you divide the train and test data by percentage. So you can have it, here's 0.2 for the test data. So it means 20% will be kept for testing, 80% used for training. And you can use any fraction between 0 and 1, so between 0 and 100%, whatever you like will go in there. And then you actually, that's why it was not then, when you can use that instance SSS, and you can start to split, and then you have to say, which data do you want to split? I want to split data X and Y, which of course were created perfectly from that make circles function that we used at the beginning. Make circles gave us X and Y, and now we apply this stratified shuffle split to it. So what that gives us is only the indices, right? It gives us the indices of the data that are used for one or the other, for training or testing. And I don't go into the details here, but you can, with those, knowing those indices for every column in your data, every feature in your data, you can then go and create that split. You have to actually execute the function, and here's a visualization of the result. At the bottom it says sample index. So from 0 to 100 is nothing but 100 data points, right? So just consecutively ordered, that's it. And on the first row of that plot, you can see the data where out of those 100 data points, whenever the data point has a label 0, it's labeled blue, it's colored blue, and whenever it's 1, so Y, whenever Y is 1, then the data point is labeled red. So we have 1 for red and 0 for blue, and then along this just axis you can see how they are divided. So this is red and blue, this is the labels, right? This is the wider labels, to what class does it belong. So that's what you want to find out with your machine learning. Now below, in those 10 columns that are black and white, so I use black and white to make it more obvious than this funny color scheme that is in the materials. It's a bit more obvious, hopefully you can see it. And black and white now is a different story. Black means used for training and white means used for testing. So it tells you which of those data points in the data set up there, where you can see what label they have, which was used for training. Like here is one that was used for training, and which one is, no, the black. Black is used for training. So that blue here is used for training, but that red here is used for testing, right? You can see how it is split up, and you can see shuffle, the random shuffle, how differently chosen data are used or withheld for testing, whereas the rest is then used for the training. So that's extremely good to remove any bias in the data And of course, by doing it repeatedly, you are sure you will get an unbiased and robust result of your machine learning using this stratified shuffle split. Just for comparison, if I just, maybe, do you know that you can hide code, right? You can hide the code away if you don't like it. If we do more or less splits, and of course we'll just change it. Let me just make the test size and the train size equally sized. Then what you can see is now black and white in the rows at the bottom are 50-50, so about 50% black, 50% white. So you have an equal amount. And this is, of course, a parameter that you can play with or you can work with. You can see how much do you actually need for training to get good test results. And yeah, you can do it to the extreme. You can make the test size 90%. Oops, where's the code? And almost nothing will be used for training and everything for testing. And you can see that the outcome might vary depending on how you do that. And that, of course, has a little bit to do also with how labels are distributed in your original data. Let's go to the next one. Let me just see what I can get it from. So now we're going into actually looking a little bit at classification, but I don't want to go very much into it because most of it is not understood by listening to somebody explaining it. It's you have to do it. You have to look at the code, modify the code, and then try to understand like this. But what we can do is we can just discuss one example. And so I copy and paste the code. Let's first see what the code does. So in the first line, I import train test split. That's sort of one split. Right now we did several instances. You know how to do several instances. Here we're just doing one, just for a demo, and we get the train data and the test data in a way that you have probably seen in our previous exercise 2 weeks ago. So train test split is the function that gives you train data and test data, and you can use the train data to train your model, test data to make predictions, and then compare with the withheld labels what percentage of prediction you actually got right. And then it makes a scatter plot and a histogram, and that's it. What does it show us? It shows us the training data and the test data. So this is just an example of the split, which looks very even here. Is that true? We go back, it says, where's the split? It says test size 50%. Yes, 50%. It makes sense that both training data and test data have similar densities. And it's using make circles. We have seen that twice before today even. And make circles, you can see that already this data set is a fairly complicated thing. Not so much, I mean, it's obvious when you look at it visually, you understand what it means, right? It's like the outer circle, the inner circle plus noise, so it blurs a little bit. But what you originally did before the advent of those machine learning tools was simple statistics. So you looked at the histograms. And if you look at the histograms of both features, they are orange and blue respectively here, and they don't show you anything of any structure that is hidden in there. You would just say, well, this is all distributed around some mean, which is probably 0. And then it has a certain standard deviation to the left and to the right. And so, of course, this is hopeless. These data come from the same distribution. So that's it. So you don't even get the idea that there might be some structure to be found. And so you can see how difficult it is to guess what data are if you just look at simple things like histograms. Or if you don't do machine learning, you will never find out what structure there is. In this case, yes, there is structure. The red are centered here, and the blue are more widely around it. But just the way it's done, it looks very unsuspicious in the histograms, And it's only in the scatter plot that you can already guess that there's a low blue density at the center and a higher blue density on the rim on the outside. So that's for the complication using make circles. You can create those kind of data where sort of there's an optimal range to predict the red label and an optimal range to predict the blue label, although it's not obvious from the distributions. Next, we now want to proceed a little bit more beyond random forest and see what else is there. So Scikit-Learn is, of course, a very beautiful library with loads of things, and every good machine learning classifier that is out there will be implemented if it's good enough, and good means tested. And so what happens is that people successively add things, so you keep looking for it. If there's a thing that you hear or read about, and it's the latest hype, or so, in all likelihood, if it's good, somebody has implemented it in Scikit-Learn, or if not, you can request it. You can say, can somebody do it for me? And probably somebody has already done it, but it's not published because there's an internal quality control process where experienced programmers check whether a new algorithm or a new model is actually better than what is already there. So what we do here is we import a number of classifiers. You can see all from Scikit-Learn. We have ensemble classifiers, decision tree classifiers, support vector classifiers, neural networks, k-neighbors. So k means okay neighbors classifiers, or basic thing that you will read about in any machine learning textbook if you go to computer science. But what we have here is we have sort of put them conveniently, packed them together into a dictionary. And that is to use them all at the same time. Probably you have seen it in the materials, how you get, in this case, eight figures from 8 classifiers. You can do as many as you like. And to sort of handle them one after the other, we put them in a dictionary. And the dictionary, you recognize maybe the curly brackets, that's a dictionary. And you have a key, which is nothing but a string, which is the name of the classifier, so-called random forest, other boost, decision tree, SVC, multilayer, and so on. This is just the name of the classifier. And then comes the actual class, the actual class that you imported, somewhere here imported from Scikit-Learn. And in this case, we instantiate each class, giving it defined random state, means we prepare it in a reproducible way, although random numbers are used internally. So that's all. The classifier, so to speak, the instances are the values of the dictionary, right? So corresponding to the name in the key, you get the values in the dictionary. So it means you can iterate through them. Right, and then we do a little bit of let's execute this code. What is the next thing? We make a grid. This is just a simple mesh grid like you have had it before. We did an exercise 2 weeks ago. I think it used mesh grid. Here it uses mgrid, but it's essentially the same. It's a different function from NumPy, but it's the same thing. And we can then see, what can we see? This is already the code, which now means take the data that we have used above, train the classifier on the training set, use the test set for prediction, and show me what percentage of data are being correctly predicted. And here's the result. So maybe you remember from the materials what that is, what the interpretation of this is. I have only plotted the test data. So the dots is a scatter plot of the test data. We have circles make 2 features. So that's only, a state space has only 2 dimensions, right? So X and Y, the horizontal and the vertical coordinate, encompass all possible values for our data. So this is the state space complete. And so we can see the result of classification in the plane in this case. And the result is given with that gray area. So the classifier is colored according to where it predicts label 0 and label 1. So let's call the outside label 0 is then left white. And if it predicts label 1, this is shaded gray. So the shading is done with the mesh grid. You remember, right? You can have that state space sort of shaded by using the mesh grid. The dots are the actual data from the test set, the ones that were predicted, and then the score above here, sort of a basic score, tells you what percentage of predictions was actually right, comparing with the withheld labels that were known in the background. So what we can infer, if you remember the theory, is that 50% is chance level. We have two labels, right? You predict either 0 or 1 anyway. So 50% is what you get if you don't know anything about your data. And if you get everything right, you predict 100% or 1 in the scoring. So what can we see? Just go through them one by one. We know our friend the random forest is 0.74, so that's above 0.5. It's good, but it's not perfect. It's not 100%, obviously, because of that high noise contamination. It's very hard to make a boundary that separates blue from red. And so you can also see that the gray area is kind of fuzzy. And you can also imagine these are the labels. This is only gray and white. This is not probabilities. You can try and use the code to put in the probabilities. You will see it gets even more complicated because, well, the algorithm tries its best, but this is the best that it come up with. And you remember doing different train test splits. You can also check how robust this result is, but you get a good idea. And then other boost is nothing but on top, it's an ensemble algorithm, the random forest, and on top you can sort of try to improve things by differently putting weight on the results and sort of summarizing and trying to get the best result, either as the optimal result that was found or as a mean of the results that were found or whatever it is. So boosting images, something on top of the random forest, doesn't really improve things. And then we have the extra tree algorithm, which scores slightly lower, and we have other boosts with extra trees, gets a little bit better and brings it back to the range of the random forest. So they're very similar. If we look at the gray distribution, then our number 5 down here, the decision tree, seems to be more fuzzy or sort of less precise, and it's not a compact decision range, so less generalizable, we typically say, because it means like a straight gray line, a horizontal line, is probably just nonsense. It's an artifact of the model training. It's nothing to do with data features. So you can see already artifacts that come in from the way the optimization algorithm struggles with that complex data set, with that noisy data set, and what the output looks like. So overall, the scoring is also a bit lower. And then we have a very nice result, I think, very beautiful results for two of them. They support vector classifier and the neural network that both have compact shapes, compact shapes. So other than the previous, the ensemble and the decision tree algorithms, these seem to be trying to preserve a compact shape for the border between the red and the blue. Of course, it's not true. There's errors associated with it. But if you look at the scoring, they're actually pretty good. So they are slightly above or in the range of the random forest, and they have a more generalizable, more compact shape. So maybe preferable in this case without any other tuning of the features. And also a nice example of a failure is the support vector classifier with linear basis functions, which sort of assumes that you can use a straight line or linear functions in order to separate the two, which of course by design of the data using make circles is impossible, right? You can't separate a circle within a circle by using just a straight line, whatever inclination that line has, or even if you bend it, it will not work. And so this here, support vector classifier with linear basis function scores about chance, so has not learned anything, and you might as well throw your coin or just use a random number generator to predict, or just not do it at all. So you can see how in support vector classifiers, it's of course of key importance to know what to expect from the data and to make a good choice of basis function, because radial basis function, RBF, radial basis function means so there's an inherent bias towards circular distributions. And that works nicely, and you can try with other types of data, but it sort of is biased towards this. But because we have used circularly distributed data, this is kind of a good match. And when you don't know how your data are, so you try different things and see which one scores better and where you are on the better track. So what else can I say here? So these have different advantages, disadvantages, and of course you would then sort of not be content by just doing this, but you would try to see how these score if you do different settings of the parameters. And I don't really want to do much, but we can just make a test size very large. So use a very small set for training, use 10% of the data for training and keep 90% for prediction. So we have much less to train on. So it will be much harder to discern any structure. And we have a lot to predict on. So we'll get a lot of predictions and we'll get a good statistics of whether these predictions are good or not so good. So you can see a little training data. So that's your sort of your small data in contrast to big data. And then like something that you have today, and then a large number of patients coming in over the next few weeks, and you want to predict them all. We'll see how that works if you have only very limited amount of data previously to train the model. So see how that works. And you can see overall the impression from that result is just very quick demo, but nevertheless, you can see, well, it's actually not too bad. If you thought it might sort of drop out and fail altogether, it's not quite true. And I want to just mention that, of course, the linear basis function will still be bad. It was bad before, will still be bad. But for example, the radial basis function doesn't really do a bad job, even though we have very, very limited data and large set of data to predict. It still scores around 77% here, which is actually not bad. So it seems to be better than 50%. It's way above that. And it's not so bad. We know what the true distribution is, right? The red come from the circular distribution inside here. And it's not quite bad, right? The compact shape is still preserved. It still didn't fizzle up like decision tree, or in this case also the random forest algorithm, and similar to the neural network. And the fact that the circular shape is now distorted, is more elliptic, is of course due to the fact that you have so few data points. So you can't really tell from those few data points what the actual shape of the circle is. So you go wrong, but not so bad. So you stay quite close. And these are sort of the things that you only get from experience, from working with properly prepared data, and then making those adjustments that I have given you glance at. So that's my take on this thing, and I encourage you to do those kind of experiments. which will first of all help you learn coding, because you need to take the code and modify it, but you will then start to see where you fail. Like, are you able to make this whole picture with, say, 12 classifiers? Can you make 4x3 images, 12 images? See whether you can achieve that, or just reduce it to 4, go down from 8 to 4, and so on. Learn about how the images are produced. Can you make different representations, maybe a 3D landscape, and so on, of the mesh grid using the probabilities? All sorts of things that you can try. Just feel free to go into it and work with it. If you have an idea that something else that's not shown here might be interesting to know. And of course, the major thing to do is bring your own data or get data from somewhere with labels and try something, and let us know if you don't get good results. So interestingly, I had an inquiry, was it just yesterday, I think, of someone who had tried to use some of these algorithms and had the problem of having very few data that are labeled of one type. So if you imagine we had this training and test data where we, by definition, by the way this function was set up, always had 50% labeled red and 50% labeled blue. Of course, in a real experiment or in a clinical setting, you might have like loads of control data, but you have few patient data. For example, rare diseases, right? You have few patient data. And you will see that these algorithms actually struggle quite a lot if you have uneven numbers. So we have it 50-50, so everything works very nice for demo, but things might get much worse. Not only small numbers of data, but also uneven distribution of labels. And then there's other things that need to be done. And so you have to weigh, and you can imagine the problem if you have only few red labels here, if they are mostly blue labels, if 80% of the labels are blue, then what you will do is you will just predict blue in every instance, and you will be mostly right. You will be right in 80% of the time, so way above chance level. So you have to correct for that, and have to make sure that the correct prediction of a red is weighted much stronger, so that this is worth more compared to the blue prediction, which is sort of trivial because most of it is blue. I have a different piece of code prepared for you here, where what I want to show you a little bit, just sort of schematically or as a sketch, how the random forest algorithm works, right? So we have, so in a sense, cheated. We have imported the random forest and then instantiated it and used it to train, and blop, there's all the wonderful things. But you might ask, how does it actually work? What does it actually do internally to find out whether or no predictions are good or bad? So here's just a little bit of an illustration. And for this illustration, I have defined a function is just a plot, just so that we don't need to see. The only thing that we have is I have created some data according to a rule, and I'll display the data in a scatter plot. Right? You've noticed that scatter plots, or the so-called state space, is our sort of our dimension to understand when it comes to machine learning. So both data sets, I have a data x1 and x2, which have then the corresponding labels 0 and 1. And I have created them such that they are both the same. And if I now plot them in the state space, I've taken the data from the same distribution, and I have plotted the first feature versus the second features. We have only two features, so that's all there is. And such that you can see the scatter, and it tells you that this is, well, I don't know what you take from it, but they're uniformly distributed. If you take large numbers, and like if you take 500, you can see It's actually uniformly distributed, so there's no dense red area, blue area. So just make a few points only, so you can see how they distribute. And there's, of course, nothing that you can do with classification in the sense, how can you separate red from blue? Well, you can't. And so what random forest does, or the algorithm then, is sort of given the task of optimizing a separation of this gray field into two areas. You remember from before, we had white and gray, or yes or no, or sort of define two areas that have labels that correspond to the data distribution, as such that you can, from knowing where the data point is, already predict its label. And so the way the random forest works is it tries to divide this state space here, that gray area, into two parts. And it does so initially at random. So I don't know what a random number you will get, but I just say 0.5. I just divide it in the middle, but this is just an initial guess. This is just because I like 1/2. Nothing else. And so what I've done is to just put in a line at 1/2. And so the algorithm now says, oh, now I need to know. No, now what I have done is with this line, I've said left is one box and right is another box. And these are the labels 0, say left is 0 and right is 1. Is it good? Right, and then we have supervised machine learning, so you provide the labels, so the algorithm can check against the labels, which are here color-coded, red and blue. So what it does, it now takes each box and makes a quantification of the degree of disorder in that box. So disorder, it's called entropy. Technically, it's an entropy. Maybe you've heard that. Entropy is the measure of disorder and inverse measure of order, if you like. And so what it looks for is how clean is that box. So it just counts the number of red labels and blue labels in the box. You take the left box and then you have a couple of blue dots and a couple of red dots. It counts the number and it creates it calculates the entropy. And entropy is probability times log probability. Can look it up. And the entropy will be 0 if that box is clean, namely if there is only one color, and it will be 1 if the number of red and blue are equal. So if it's maximally disordered, that is same number of blue and red dots here, then the entropy will be 1, very disordered. And if it's 0, then it's either blue or red. Right? So you can see what happens. And this algorithm then, after having done it, in this case, will find maximal disorder left and maximal disorder right, will then start to move this line and move it to 0.2 and do the calculation again. And now it has red and blue on the left box and red and blue on the right box, and then compares the entropies. You'll say, well, actually, the entropy didn't really change much. So what I need to do, need to go to the other side and then do 0.8, and it finds, well, still doesn't really improve. So in this case, I don't know where the algorithm will be sent up, but you can see there is nothing to find. So the algorithm will also at some point just give up and say, well, I'll predict at random, or it's the 50% that we got with the linear basis function above. So now I have created a distribution that is actually different. I'll just get this code away here. Taken a distribution that is different insofar as the vertical feature, the second feature, is still what it was before, but now on the horizontal feature, there's a split in that the blue have small values and the red have large values. Now, if I go into this, and I put my line like before it initially at 0.5, what you can see is this. The red box is now clean, pure. This is total order. This entropy is 0. On the other hand, the blue entropy is good. There's a lot of blue points there, much more than red points, but it's a little bit contaminated. So it's above 0 And so that's what you get. So it's quite good. You have the red separated from the blue, but there's some contamination in one of the boxes. So it then moves the line, right? The algorithm then picks another number and moves it, say, moves it to 0.8. And then you calculate the entropy and see, oh, things are now worse. The red box is still the red box, still perfect, but on the other hand, this entropy has increased because now there's equal amounts or nearly equal amounts of red and blue. So the algorithm says, oops, that was the wrong direction, go in the other direction. So you go to 0.2, you try that split, and then you see, yeah, it's not so bad, but the blue is now perfect, but the red is now contaminated. So there's some disorder here. Only one box is like before. We had it already perfect, but now the other box is contaminated. And then it will fiddle around and go a little bit in the direction where the entropy decreases, right? You get more order and go in smaller and smaller steps. And you get better and better every time, seeing if the entropy goes down, you're good. If the entropy goes up, you're bad, go in the other direction. And then this line that I use is called split. If I then use the line at split, then it will be perfect in this case. And you have perfect order, perfectly separated blue from red. So that's the optimization that the random forest algorithm goes through. And of course, it does so not only horizontally, like this is just a demo, but also vertically or in any other dimension that you have. For every feature, you can do this. Finished. Thanks for watching today. Take care, everybody. Bye, and see you next time.